Excellent. Welcome to the last talk of the day. The speaker is Pietro Belotti from FICO. The floor is yours.
Thank you very much. So this talk is about solving quadratic optimization problems. That is, well, not too far from what Miguel and Erling just talked about. I will talk about nonlinear problems where the constraints are convex quadratic. I'm here in my capacity as both Politecnico, so Technical University of Milan staff, but also I used to work collaborate with FICO in their FICO Express software. So I will relate on experiences that I gathered as a developer of FICO Express. So the outline is a bit crowded, but that's because as we'll learn pretty soon, a solver for general quadratic optimization problems with possibly discrete variables is a bag of tricks, and this is similar to what happens for mixed integer linear programming, where one single method doesn't do everything. You need a lot of small algorithms that actually take care of classes of constraints or classes of problems, etc. So I'll try to explain a little bit what we do, and the algorithms that are used in the solver are relatively simple versions that can actually, though, scale up to relatively large instances. One of them is bound reduction, so taking the bounding box that is initially in the problem and trying to tighten it in order to make the solution a bit faster. Dual reductions, that is another type of pre-processing technique. There is also outer approximation, which is a fundamental algorithm in solving mixed integer quadratic problems. And then there's a couple of other interesting algorithms like perspective reformulation that have a slightly more interesting mathematical basis, and then cone reduction and cone decomposition, which also are derived from the literature. And finally, there's an idea that we actually started using a couple of years ago, and that is, in fact, relatively simple to implement and surprisingly, linking two different aspects of optimization. So zero half cuts that are a common form of cutting planes, and quadratic optimization. And I'll basically, given that these are all seemingly unrelated topics, I will stop at every couple of topics and actually show the impact of each piece of the puzzle. And let me remind once again that we are only dealing with convex MIQ-CQPs and MISOCPs. That is, we do have mixed integer problems. So some variables are discrete, binary or integer. Some other variables are actually continuous. But the constraints are either linear or convex and quadratic. That obviously includes second-order cone constraints. So just as a general consideration, so FICO Express is actually a solver that can tackle on nonlinear problems as well. So the class of problems I just mentioned is the target of the biggest part of the FICO optimizer. There is also part of the library that actually allows to solve to local optimality general nonlinear problems, even with black box functions. And more specifically, if we take the general class of mixed integer convex problems, that is general mixed integer quadratically constrained quadratic problems, what we do in order to solve them is apply a technique that is very similar to what we do for the linear case, that is for mixed integer linear programming problems. We first of all apply pre-solver, which is an algorithm for pre-processing the problem and possibly reduce its size, that dimensions. This is extremely important, and this is actually one of the most important components of any solver. And then there's the main workhorse, which is the branch and cut algorithm. It's the branch and bound plus separation of cutting planes. And this is where the bag of tricks comes in. That is, some of the specialized separators for cutting planes are actually very useful for solving specific classes of problems. And this doesn't stop here, of course. There's plenty of other small tricks that are used in every in every solve for several different classes of problems. So let me start introducing some notation. We'll see this sort of constraints throughout the presentation. So it's I'd rather introduce the notation just now. Let me just start with the first very simple type of bound reduction. That is, it's a trivial idea, but it works relatively well in some instances. So what you want to do is start solving do a pre-solving on an instance that contains on a problem that contains a few quadratic constraints, and they are all of this form. So you have a quadratic matrix Q. The vector of variables is X, but there is also another separate vector of variables Y that is only different in that it doesn't have entries in the matrix Q. So you have a general quadratic constraints that contains quadratic form X transpose QX plus B transpose X, and then there C transpose Y is just a different linear combination of other variables, and this is less than or equal than D. So what we could do is, if Q is positive definite, is transform that into a slightly different form where we actually get some more information about the quadratic form itself, in that we actually get the minimum, the global minimum X bar of the form, the quadratic form X transpose QX plus B transpose X, because that can be actually useful for deriving bounds, as we'll see in the next slide. So keep in mind this form of the constraint, and now let's try to understand the following. Is there an upper bound on the expression alpha minus C transpose Y? That is, let me go back. Is there an upper bound on the expression that I get from the right hand side, and I subtract C transpose Y? If that is the case, then let's call it beta. And that means that you now have a quadratic constraint that is something like this, that is slightly more suitable for bound reduction, because now we can simply, we have a convex constraint that are definitely surely finite set of values, so on which we can actually compute the minimum for all the variables. And this is similar to other techniques used in general nonlinear optimization, but this can actually be useful in quadratic optimization as well. Once you actually have this form, the quadratic form in this version, then computing all of these minima is extremely easy, because it only requires solving a linear system where the coefficient matrix is only an L matrix that results from an LDL decomposition of Q. And so this is relatively fast. I can actually give relatively good tightenings of all the variables in the quadratic form. So this obviously takes some extra preliminary operations, but it can be useful. There's another way of trying to reduce the bounds in MIQ-CQP, and this is actually something that would work for non-convex quadratic problems as well. And it arises from, well, isolating a single variable. Let's call it, well, let's take x1, and then let's just rename it y for the sake of clarity. At least I hope this is going to be clear. But basically, you can then rewrite any quadratic constraint as follows. You take the quadratic coefficient for y square, which is q11, of course. And then you have a coefficient for y that is going to be not a constant, of course, but rather a linear expression, which is given by this summation plus b1. Because I consider obviously the linear part as well. And similar for the rest of the summation, including the x's. This is going to be treated as a, well, not as a constant, obviously, because it's a function of all the x's, but it doesn't contain y, so I'm going to ignore. I'm going to just take it as a pseudo constant, let's call it like that, value. So you basically have a rewriting of the constraint, of a quadratic constraint, that is something like this. And obviously alpha is constant because it's equal to Q11. Gamma is non-constant because it depends very much on the bounds on the x variables. And the same holds for delta, which is just going to be this summation minus d. So you basically have an inequality, quadratic inequality in y, although the constant, the coefficients of the linear coefficient and the constant term are obviously not exactly constant, but rather they vary in an interval. So it could be just seen as an it could be seen as an exercise to find out how you can tighten the bounds on y square, and it's just a matter of finding out where to find the minimum of that expression, depending on the coefficients themselves. But basically, the solution is as follows: if alpha is equal to 0, which could happen in some cases, then you can tighten the lower bound on y if the gamma, the upper bound on gamma is negative, and vice versa. You can tighten the upper bound on y if the lower bound on gamma is positive. If alpha is actually non-zero, then you can still do something on the bounds, and you could easily tighten the bounds on y. Keep in mind that obviously this is a heuristic approach. It doesn't necessarily give you the same nice results as the exact approach I showed in a couple of slides ago. And it actually can turn out to be quite expensive. Just to give you an extra detail, this is currently implemented in Express, but it's switched off most often. It's often not active simply because it's we found out that it doesn't exactly give a lot of great results. So the third part of this pre-solving mechanisms I wanted to talk about are basically what we call dual reductions. And they can be simply seen as a generalization from the linear world, that is, from the mixed integer linear problem solving, where you start with a linear set of constraints and the linear objective function. And it's a very simple technique, and actually very fast to fix one variable, which can happen very often. A variable xi can be fixed to its lower bound if we are minimizing, of course, and its coefficients in the objective function is non-negative, and also for all of the constraints, these conditions hold. That is, all such conditions must hold in order for us to be able to fix xi to its lower bound. So for if it's a greater than or equal to a constraint, then its coefficient must be non-positive. If it's an equality constraint, there must be no coefficient, etc. We could even end up seeing that actually L, the lower bound, is negative infinity, which basically means that either we need to eliminate the constraint, or just saying that the problem itself is infeasible. The same holds for, well, the upper bound, of course. You just need to invert a couple of signs here and there. This is also a very simple technique that's used in mixed integer linear programming. And so the generalization to the quadratic case is relatively simple as well. We can still consider, obviously, the coefficients and in the objective function and in the constraints. But obviously, again, the coefficients won't be exactly constant. We need to check the lower bounds and upper bounds of the expressions for which the y variable is multiplied. And so we need to do this in this way, basically. So if we take this function and we find, for example, that it's monotone non-decreasing, which happens when this case is true, when this expression is greater than or equal than 0, or we actually find that it's minimum over the whole interval of the variable in that we are looking at is YL itself, which means that these conditions must be true. Then we can still fix the y variable to to its lower bound. Obviously, these conditions are not exactly as straightforward as for the linear case, but the generalization is relatively easy. So this is a preliminary part of the solving of mixed integer quadratic problems. I'll show you very few test results. I won't show you any specific instance, but there are a few sets of instances where one can take out some instances and try these problems on. Obviously, depending on the type of instance, the results will be very different. So these three, so there are three techniques: the exact bound tightening, the heuristic bound tightening, the quadratic dual reduction we just looked at. And for this set of instances, which is part of the benchmark that's used by Hans Mittelmann in his website, and that's available for most solvers, although Express no longer is part of that benchmark. We can basically see the following. There is actually not too much of an effect of these techniques. That is, we don't have any instance that improves its performance by more than 10% with these techniques. But we can only see a slight improvement in geometrical mean of the whole of all the solution times for all these instances. And this is for this set of instance that contains 23 of them. There are other sets of instances on the same benchmark where, in fact, we do a lot better. And so we do much better when we use both, when we use the exact bound reduction. So we can easily see that some of the instances actually improved by more than 10%. The same doesn't happen if we use the quadratic reduction. That is, we don't have such effects there. For other sets of instances, the results clearly vary. Here, the effect is slightly less than the previous set, but more than the first set. And the same holds for yet another set of instances. This last set is a specific case where we have a lot of instances, 1600 or almost 1700, but where the objective function only is quadratic and the constraints are all linear. So I hope this is, so I would like to close this part. I can stop in the meantime if there are any questions, but the next part will be about solving the actual problem after it has been reduced by the pre-solver. So let me know if there's any question, otherwise I can just proceed. So once we have a problem that has been pre-solved and a few variables have been fixed, and then now we have a problem that might be reduced, but it's still quadratic. Well, in the simpler case where only the objective function is quadratic, and some variables are discrete, the basic technique to use there is branch and bound, where every node is solved with a quadratic simplex. The quadratic simplex is a version of the simplex method that can take on problems with a quadratic objective function. Obviously, doesn't work with quadratic constraints, but it's still relatively efficient with regards to so solving a node problem, solving a single branch and bound sub problem, in that it doesn't require as many iterations and as much time as an interior point method. In the more general case, instead, where we have quadratic objective function and quadratic constraints, we are somewhat bound to use a barrier method or an interior point method to solve every branch and bound node problem, simply because, well, every the continuous relaxation of every node problem is in fact a quadratic problem, quadratically constrained quadratic problem. This is in theory. That is, we would have to do this in these cases. And the big disadvantage with this, although it's not always the worst thing to do, is that every node, every branch and bound node has to issue a new, has to start a new optimization, a new solve through a barrier method, the interior point method, which can be rather inefficient because the barrier method is extremely efficient when done once. But if you have to repeat the same solve through every branch and bound node problem, this is very inefficient. And so what I just said is not only theoretical, but it's verified in practice, and it's true most of the time. So what is actually done is a slightly different technique that actually turns out to be a lot more efficient, which is called outer approximation. And I mean, it's been mentioned on and off with different names, but it's basically it's an extremely simple technique that takes one nonlinear constraint that we just defined very generally as a g of x lesser or equal than 0, with x it could be it's a vector of variables, and it takes any point x1, x2, x bar 1, x bar 2, etc., which may or may not satisfy the constraint. We don't really care whether they do. Then a valid LP relaxation. So a relaxation of the set of points satisfying this constraint is going to be a set of points that satisfies R constraints defined by the Taylor series approximation of the function g less than or equal to 0. Let me add the first degree Taylor series approximation. So you take the value of the function at a given point, and then you compute the gradient of that function at the same point, and you multiply it by x minus that point. If you do this, well, you will get a polyhedral relaxation of your constraint, no matter where the R points come from. Well, I very much like to use visuals to explain concepts, although this is probably a very easy concept for everyone here. But suppose that the blue area is the set of is a ellipsoid that is the feasible set of for the constraint gx less or equal than 0. Then you take any point x bar 1 and you add one such linear constraint. And then you do the same thing for x bar 2, etc. And you do it for all the points you have. Then the resulting set will be this, well, assuming, of course, that x1 and x2 are also non-negative. The resulting set will be obviously a superset of the part of a ellipsoid that is on the first orthant, and it's a superset that is also polyhedron, which means we now can use linear programming techniques in order to find the lower bound for every branch and bound node. And this is so I don't have any follow-up slide on this, but there's a fundamental consequence of this in that if we apply this sort of technique to every branch and bound node, there is a huge impact on the solving time, simply because now every time we create a new branch and bound node, all we have to do is possibly add new outer approximation cuts and resolve using the same algorithm that is used in mixed integer linear programming, which is the dual simplex. This makes a huge impact on efficiency, because dual simplex applied on a sub problem where the only change is an extra constraint is going to take a lot less than restarting the whole interior point method on the branch and bound node. So although it's a very simple technique, it actually has a very large impact on the possibility of solving many of these quadratic instances. A technique that may not have as much impact, but it's still very interesting and actually can solve some of the problems in public benchmarks, is a technique that uses the so-called perspective reformulation, which is connected to what Erling talked not more than an hour ago when referring to the perspective functions. My description here is slightly different because it's a bit more, it might be a little more down to earth and not as sophisticated as what Ellen said. But the function, basically, the technique pretty much works as follows. Suppose you have a set S1 that is described by the set of points x in Rn such that f of x is a function, f of x is less than or equal than 0. And suppose there's another set S0 that is just defined by a single point x bar. And let's suppose for now that, well, in general, f of x is a non-homogeneous polynomial of degree k. We can easily think about this as any quadratic function, non-homogeneous quadratic function. But for now, we can easily think of, in general, non-homogeneous polynomial. And now the problem definition itself tells us that there is a binary variable z such that if z is equal to 0, then the model enforces that x must be equal to x bar. And instead, if z is 1, the binary variable z is 1, then x can easily roam around in S1. So it's no longer as strictly fixed to x bar. So if that is the case, and we'll see an example later, which I find relatively interesting, is the technique consists in the following. Then take the non-homogeneous polynomial and multiply all the terms of degree less than k by a sufficient product of z. So by z to the power of, whatever is needed to reach homogeneity. What you get is now a homogeneous polynomial g of x, and the constraint g of x less or equal than 0 is as valid as f of x less than or equal to 0 was. And this time it takes into account, obviously, the fact that for z equals 0, then the constraint can be ignored. There is a citation here with basically the technique in much more detail by Günlük and Linderoth. There's also another citation by Frangioni and Gentile. So Claudio Gentile and Antonio Frangioni describe a very similar technique in pretty much the same time. So again, I'd like to give you a visual representation of this because I find it extremely interesting. So if you have three variables, our binary variable z, and then two variables x and y, and we know that for z equal to 0, then the solution to the problem imposes that x and y are both equal to 0. So basically, the origin, the red dot, is one feasible solution of the problem. If z is equal to 1, so if our binary variable is equal to 1, then we allow x and y to be non-zero, but we impose the constraint that y be greater than or equal to x squared. And well, if we write the constraint just like that, and then we enforce the fact that z equals 0 implies x and y both equal to 0, then what we get is a geometric representation, which is basically just a cylinder whose basis is basically this parabola x squared, less or equal than y. However, if we apply very simply the perspective reformulation technique I just presented, I just described, all you have to do is multiply the right-hand side y by z. And what you get is actually, if you try to represent this, this is a rotated second-order cone, which will exclude everything in the cylinder that was basically around here. And so this is the nice thing about this is that it allows us to eliminate a lot of uninteresting solutions from the problem just by changing a constraint and not even adding one. And the constraint that we added is actually a rotated second order cone, which is one of the nicest to deal with when solving MIQ-CQPs. There are more complicated constraints. There's an instance in a public benchmark, which is also very interesting because it contains a constraint that is described like this. So y must be less than or equal to x divided by 1 plus x, where x and y are both non-negative. So if we massage the constraint a little bit, so we start taking stuff on one or the other side, what we can get is actually, and this is part of what Elling was describing before, that is, if you see a nonlinearity like that, there's a good chance, this is what happens in a lot of min-lp-lib instances, that this might be described using cones. And this is the case here, that is, this is this seemingly just nonlinear constraint can actually be turned into a second order cone, which is a very specific class of constraints that can be very, very useful. And it's not only a second order cone, because as you can see, there's a one here, which makes this constraint actually a non-homogeneous polynomial, well, non-homogeneous quadratic constraint. So what you could do is the following. We also know that there's, for that specific instance, we also know that there's a variable z, which implies x equal to 0. Now, this is not too important, but if x then is equal to 0, basically the constraint is useless. It only implies that y is less or equal than 0, but this is totally this is trivial, which means that if we apply perspective reformulation, we can substitute this one here with a z and obtain actually a stricter, a tighter constraint that is going to allow us to solve the same problem, the problem from this class of optimization problems, much more efficiently. So another technique, probably an even more important technique than perspective reformulation, which, as I said before, is not applicable all the time. It doesn't have as much impact as other approximation, but it can be useful in some cases. This technique I'm going to show now, which is again very well known in the literature, it has been established. Well, it is actually easy to derive with the simple algebra, but it can also lead to drastic improvements in performance. So if Q is positive definite, then it can be decomposed as a with L transpose decomposition as a product of two lower triangular matrices, L and its transposed, which means that the quadratic constraint that we write here can be rewritten as a set of linear constraints. So this is the first linear constraint, which is a transformation that takes x and returns as y. A second order cone constraint derived by just taking the norm, the square norm of the y vector, and making it less than or equal to 2 times z times t. And then rewriting the original quadratic constraint by basically just putting in z. And well, the t variable was actually just added there for not much purpose really, because it's set to be a constant equal to 1/2. This you may think that this has a few problems. Namely, it introduces new variables. It doesn't really make the problem linear because we still have a quadratic constraint, which is this second order cone. And this third thing is actually quite true. Depending on the quadratic matrix Q itself, the L may not be that very well behaved. But this technique basically allows us to turn a second order, a quadratic problem into a second order cone problem, and these things actually can do a lot for performance in a lot of mixed integer quadratic programming. So with this, well, this is one of the techniques I wanted to discuss because I find it, again, a very simple idea, but in practice it works extremely well, especially with large instances where one has decent algebra routines that can actually do the job in a decent time. The last technique that actually is follow-up to the one that I just discussed is well, one way to decompose cones into smaller cones. This is again related to what Erling discussed, and I'm really glad we were placed back to back. So if you have an MISOCP, a mixed integer second order conic programming problem to begin with, where you have a linear objective function, a bunch of linear constraints, and then X is supposed to be a member of a Cartesian product of cones, of second order cones, so there's Lorentz cones. Then you can do a lot of different interesting things. I give again here the definition of second order cones, but right now between Miguel and Erling's presentation, I think we already know what they are. But basically, just the difference between the second order cone and the rotated second order cones is just the fact that on the left hand side here, I only have one variable and or a product of variables. But what is really interesting in these cases is that if I stayed with this sort of cones, if I kept them into the problem, I would easily be able to apply other approximation. And you can imagine how the other approximation cuts would look for this second order cone, for this ice cream cone. And these cuts, the other approximation cuts, can actually be efficient and can actually give good results. But there's a technique that can actually improve even more the performance, and it's the following. So you take let's take the second order cone, the standard second order conic constraint, which is the sum of xi squared less than or equal to xo squared, and obviously we must have that x0 must be non-negative. And this technique has been documented by Juan Pablo Vielma and co-authors in this very nice paper. And what happens here is that you can transform this cone, which in practical applications can actually contain a lot of terms. That is, K in practical applications can be very large, which may have some effects in numerical stability. You could rewrite this problem, rewrite this constraint as the following set of constraints. Let me write it down here, and then we can discuss it together. But basically, what this turns into is a linear constraint, because you introduce new variables yi. The sum of these variables must be equal to x0, the original x0 variable here. And then what you add is a bunch of new rotated cones that contain the xi square variable that was used in the original summation. And then only what you need is simply just the non-negativity conditions on yi. This is really a very easy technique, and it's very easy to implement. But curiously enough, if you do this and then you apply other approximation on the smaller cones, the performance can actually do a lot. For some instances, of course, there are some instances where this does better. If we take the same set of instances we looked at the beginning, what I can show you is well, a summary of a benchmark comparison where we take all these classes of problems, of which we have the cardinality here in the second column, and then I can tell you what the instances that were solved before the 2-hour time limit, and these are given here, through the default behavior. So if we, by default behavior, impose that all of the techniques that I showed before, then what you do is, what you can observe is that the general behavior of the solver itself is relatively good. I can also show you, however, what happens when you exclude some of these techniques. So if the last one that I showed, the second last, if you exclude the technique that takes a quadratic constraint and transforms it into a cone, then the performance doesn't get much worse. It actually improves in one set of instances, although this is a very peculiar set of instances where all variables are binary. Things get slightly worse when we don't actually decompose an econ, because there's only one instance here that is not solved with respect to the default, with respect to the algorithm, when we also exclude con reduction. As you can see from the last two columns, though, what happens when you actually exclude outer approximation? You impose that the solver uses the barrier method, the interior point method at every node. There's a lot of things going on. That is, a lot of instances are going to perform a lot worse than before. The very last column instead is a slightly is a different sort of experiment, where we forced outer approximation on every single instance, even when we actually tune the solver not. We would in general tune the solver not to use outer approximation, because we found that it would actually be detrimental. And if we force outer approximation, which which can be done through parameters, the performance is not so good either. I mean, the second last column tells you that outer approximation is actually very important in solving these instances. That is, turning the node solver from an interior point method to the dual simplex method actually does a lot for towards solving these problems to optimality. Okay, so slightly different performance comparison, but instead of telling you the number of instances that actually solve, I'm going to show you the shifted geometric means over all the solving time for all of these same classes of instances. The shifted geometric means is a variant of the geometric mean, where we shift every value in the geometric mean by 10, and then we take the result and we subtract 10 from it. The shifted geometric mean is commonly used in performance comparison in optimization, although it does have its own drawbacks for using. And well, what you can see here is that there can be actually a drastic improving when using all of these techniques. And this set of instances shows it probably the best, because not using any of the techniques that I discussed before leads to a much worse performance in terms of time throughout the set of instances, of course. I'm done with the second part. This is basically what happens to the solver as a whole. So that the core of the solver contains all of these tricks. The fact that we activate them or don't activate them depends very much on the type of instance. With the solver itself, is tuned every time to understand whether some classes of instances deserve to use some of the techniques, and some others may not. But this is what happens roughly on top of the branch and bound that is used for solving the problem. And these are all techniques that work pretty well on quadratic constraints. If there are no questions, I don't have too much time actually, but I have a third part I would like. Yes.
So you were saying that basically you are converting a quadratic program into a second order cone program, and that you like the SOCP better than the quadratic program. Yet before you were saying that you don't like to use barrier methods to solve those because you can't warm start them, and you can't easily update the data without rerunning the whole interior point method.
That's correct.
So why do you like the SOC method better than the quadratic?
I think
both by barrier method, right?
Right. So I think the advantage here is, I mean, it's very simple. When you have a, okay, now let's take this quadratic problem, this quadratic constraint. Applying outer approximation on a constraint like this is going to give you a very large constraint, a very large linear constraint, possibly including all the variables. And in fact, you're going to have a lot such constraints, at least one in every branch and bound node, all of them have n variables, where n is the number of x variables, right? This is really bad for simplex methods. That is, if you have, so if you fill up the simplex method with a problem that has very dense constraints with a lot of variables, the simplex method is not going to like it. This technique instead is basically taking a quadratic constraint and transforming it into a cone, which makes it a lot easier to solve. That is, the other approximation for this problem, when coupled with the cone decomposition that I showed the slide after the slide, the subsequent slide, is going to return, is going to create other approximation cuts that are a lot sparser. Sparsity is a big has a big impact on solvability of the problem.
I see. Thank you.
You're welcome.
Are there other questions?
Yes.
Question. If not, then please continue.
Okay. Where are we? Okay, here. The very last part is on a very peculiar set of problems where, well, we may have both quadratic objective function and constraints, and also linear constraints, but something special is that all variables are actually binary. In these cases, what we have is that we have one extra possibility. That is, we don't necessarily have to treat the problem as quadratic, because now we know that all variables are binary, and we may know what to do in these cases. That is, take every product xi times xj. We know it's binary, so it can only have two values itself, so 0 or 1. And we can introduce a new variable yij. This is, again, you may have seen this in the other presentations today. Apologies for the repetition, but I think it's these problems are so important, that they're so prevalent in industrial applications, that you can see this sort of transformation very often. Whether what you use with this transformation or with this relaxation, it can be very different, but this is a sort of operation you do on the instance that can be done for multiple reasons. So if you introduce a variable yij now, you can rewrite the quadratic form x transpose qx this way. This is the Frobenius product of where you have two matrices of the same dimensions, q naught and y. And this Frobenius product is simply the product of every element of q, the sum of all the products of all the elements of q naught with the corresponding element of y. So q11 times y11 plus q12 times y12, etc. But it's linear. So it's basically an objective function is just a weighted sum over the y variables, and it's going to be linear. And the same holds for this set of formally quadratic constraints. They are all linear now because I introduced the y variables. The elephant in the room, so to speak, is now a different type of constraint, which is this rank 1 matrix constraint. Again, this is something we already saw today. That is the compact way to represent all of these constraints, where we want yij to be equal to xi times xj. And of course, we have our set of linear constraints. What we could do here is, well, this is a non-convex constraint. We don't like it. What we could do is, well, a technique that has been, the general nonlinear case is due to McCormick, but I think in the binary case for logical sort of relationships was also introduced by Forte. And it's the following: if yij must be equal to xi times xj, then we can easily just say xij must be greater than or equal to xi plus xj minus 1. Xi obvious xij yij must be greater than or equal to 0. Yij must be less than or equal to xi and also xj. Writing these four constraints will give you a set of triplets xi, xj, and yij, where all vertices are going to be feasible for the product. That is, all the vertices are such that Yij is equal to Xi times Xj. Again, this is a technique that has been around forever, and the problem here is, once again, once you have a technique, you have as a developer, you have a very important decision to make. Do I use this technique or not? That is, now that I have this sort of transformation, now that I transform this problem with new variables y, is it actually worth it? Or if I have this such problem, do I keep it like this, and do I use other approximation with all the cool stuff that I presented before, or do I actually transform it into a linear problem by removing this rank 1 matrix constraint and just replacing it with this sort of constraints? Well, the answer is I have no idea. It's very hard to understand when one should apply this technique, because obviously there is a trade-off. There are a lot of things that need to be decided. One problem with this is that obviously a null of n squared new variables are added, but obviously those problems might be those variables might be many, but at least the problem becomes linear. So one has to weigh these two things and see whether this is actually worth it. The good thing with being linear, with the problem being linear, is that the pre-solve, the MILP pre-solve might actually wipe out some of the Yij variables. May be the case. And it could just be that also the linear constraints make the transformation trivial, or that it actually makes everything a lot more complicated. Just to mention why this is not exactly an easy task, an easy decision, there is actually a nice paper by Piero Belotti, Andrea Lodi, and Giulia Zarpellon on actually deciding whether this is good through machine learning. Because, as usual, a lot of parameters need to be taken into account before deciding whether this is the case. Okay, I'll just do this slide, and then, given that it's already 8 to 5, I'll stop. But the technique that we actually introduced, and it is a very simple technique that may already have been known in the literature, is the following. Well, we take, given the discreteness of the problem itself, what you could do is take 3 variables, x1, x2, and x3, and suppose that there are bilinear terms, x1 times x2, x1 times x3, and x2 times x3, which correspond to the 3 variables y12, y13, and y23. The Forte constraints defining them are basically given by these 3 rows. And if you just wake up one morning and say, let's just multiply all 3 of them by 1/2 and sum them up, what you get is obviously one other valid inequality. But by applying, well, another workhorse of mixed integer linear programming, which is the Kvatagomori method, what you get is, well, you round down all these coefficients, and you also round down the right-hand side. And what you get is a valid inequality that is like this. I won't go further on this. I can only show that there is actually a technique for engineering this. But unfortunately, there's not much time, but I can obviously take questions regarding this later. But it does have an impact because I won't show you anything else in the table, but basically this technique itself increases on average by 23% the performance. So it improves by 23% on average the performance on some of the quadratic instances, including the QPlib, which is also a public benchmark available online. With this, I'll stop here, and of course, I'm ready to take any question.
Thank you very much. Are there any questions from the audience? Maybe.
Hi, Pietro.
Hi.
It's over here. So I was wondering, actually, you mentioned all of these techniques and whether or not to apply them, of course, is the big question. We can see also the impact on the table. What we see as well on the table is that you have some very good defaults. That was especially visible on the previous part. I think recently you've been working on machine learning algorithms, but before that, what's the basic information you're using? Is that typically a structural problem, or are you like typically using some info from factorization at the first iteration, or how do you make those decisions basically?
Well, usually these decisions are made based on experience. That is, so we do have obviously a database of not only public instances, but also industrial customers that provide us with their own instances. And these are massive. These are, I mean, it's hard to state the scale of these instances sometimes because they're really instances with millions or tens of or hundreds of millions of constraints and variables. And we try to obviously establish a default set of parameters that is going to be good on every instance, but it's hard to state that. So one of the initial, so even before the pre-solving part of the solver, one tries to study the whole instance, and so the solver tries to see the whole instance and see whether some of the parameters need to be set to a certain value. And this, as you suggested before, obviously depends on the matrix itself, the possible factorization, how numerically behaved the factorization is, how the coefficients themselves, the sparsity of the matrix, both the matrix of linear coefficients and the quadratic matrix for all the quadratic constraints and stuff like that. But there is a significant part of the very initial part of the solver that tries to infer as much information as possible from the instance and decide what controls should be set. And there is a recent effort that we are doing that uses machine learning for this, basically tuning this. That is, I think there's a paper that recently came out by Timo Berthold, one of my former colleagues. He's still at FICO, and I only collaborate with FICO. And I think the title of the paper itself is relatively telling, and it's called "Learning to Cut." So it basically says when it's better to apply some separation techniques and when it's better not to. And this is decided on the basis of some machine learning technique. There is another couple of them in the works, and there has been another one last year published, basically on the same sort of subject. So using machine learning to decide how to decide the value of a control as applied by the solver itself.
Okay.
Hope it answered your questions.
Yeah. Thanks.
Are there